In this video, we'll talk about where eigenvalues show up in differential equations. So in previous videos, we've been looking at eigenvalues, and one question that's often asked is, what's the significance of eigenvalues? Why do we care about finding the eigenvalues of a matrix? Well, one answer is that eigenvalues tell you information about how the matrix is transforming the space, Rn. If you have a m by m matrix, it's taking Rn to itself, and the eigenvalues tell you the eigenvectors are the vectors that get stretched or compressed. They're kind of pointing in the same direction, the same line as the input. Did I phrase that correctly? They're the vectors that get transformed to scalar multiples of itself. So the transformation stretches or compresses those vectors. But there's another way of thinking about eigenvalues, and eigenvalues show up in differential equations. So in this video, you're going to have to know something about differential equations. And if you look at a linear second order differential equation, if you're taking a differential equations class, if you wanted to solve something like the second derivative plus 5 times y prime plus 4y equals 0, then there's a standard approach for doing this. This is a homogeneous linear second order differential equation with constant coefficients. What we're looking for is a function, y, such that when you calculate the function on the left, it's equal to the 0 function. So when we say that this left-hand side is equal to 0, we mean that it's just the constant function 0. Or more precisely, it's the constant function 0 on some interval. Okay, but most examples, it just means the 0 function on the entire real line. And we're looking for all the functions y that satisfy this differential equation. And one of the things that you learn is that you can try an equation of the form y equals e to the rt. And this function has the property that if you take the first derivative, it's just a constant multiple of y. It's just r times e to the rt. The r comes from the chain rule. And if you take the second derivative, then you get another r, and so that becomes r squared e to the rt. And then you take these things, you plug them into the equation, so you get r squared e to the rt plus 5 times y prime, that's r e to the rt, plus 4 times y, so that's 4 e to the rt equals 0. Now I can factor out an e to the rt, and I get r squared plus 5r plus 4 equals 0. Now I have a product. I have this function times that function is the function 0. And when that happens, I have, actually, this right-hand side isn't even a function. This is just a constant, right? R is a constant. If r squared plus 5r plus 4, that's a constant. So if a constant times e to the rt is 0, well, e to the rt is never going to be like the 0 function, right? It's an exponential function. So if I have an exponential function, and then I multiply by some constant, this constant times the exponential function is 0, that constant must be 0. Okay. So this implies that r squared plus 5r plus 4 must be 0. And now I can solve this equation because I can factor this as r plus 4 times r plus 1 is 0. So I have two numbers whose product is 0. Of course, I know how to solve this. R is -4 and -1. Okay, and so two solutions are y equals e to the negative 4t and e to the negative t. Actually, there's a theorem that says that once you have these two solutions, that all the solutions are going to be a constant multiple of the first solution plus another constant of the second solution. So C1 and C2 are just real numbers. And that's the general solution to this differential equation. So these e to the minus 4t and e to the negative t are two linearly independent solutions. And there's a theorem that whenever you have a second order linear differential equation with constant coefficients, the solution is, see, this is like the span. It's a constant multiple of the first function plus a constant multiple of the second function. So the solution set is in some sense two-dimensional. Okay. That's just part of the general theory. And this equation is sometimes called the characteristic equation. So let's call it the characteristic equation. The characteristic equation is what I get by taking r squared plus 5r plus 4 and setting it equal to 0. And notice that this r squared plus 5r plus 4, the 5 and the 4, come from the 5 and the 4 in the original differential equation. And in this video, I want to explain that this characteristic equation actually is related to the characteristic polynomial. So this characteristic equation, if I look at this is actually a characteristic polynomial of a certain matrix. So how do I get this as the characteristic polynomial? The idea is to bring in the matrices, of course. So I need some matrix. And the idea is that I can take my original differential equation, which I'm going to write like this. Okay, it's the same thing. I'm going to subtract 5y prime and 4y prime. Not that. 5y prime and 4y. So I get y double prime is negative 5y prime minus 4y. Okay. Now I can actually write this. So this is the same as the original equation. I'm just writing it a different way, right? And I also know, of course, that y prime is equal to y prime. That doesn't change anything. Of course, y prime is equal to y prime. So I have these two equations here, and I can write this actually as a matrix vector equation. I can write this as y double prime here and y prime here and y prime and y. And I can have this matrix negative 5, negative 4 in the first row and 1 and 0 in the second row. And you can check that if you actually take this matrix and multiply it by this, well, it's a vector, except that the vectors, the components are actually functions, right? I mean, these are not constants. I mean, y is a function, y prime is a function, y double prime is a function. But nevertheless, you can still express this system of, well, now I have a system of differential equations. This is a system of differential equations. Which I can write using matrices like this. So let's call this matrix A. And there's a general theorem that says that if A has eigenvectors v1 and v2 with eigenvalues lambda 1, and lambda 2, respectively, then v1 e to the lambda 1t and v2 e to the lambda 2t are solutions to this equation. Let's call this vector x. So this is a vector with functions as the components. Then this second vector here is going to be x prime. I take the derivative. If I take the derivative of y prime, I get the second derivative. If I take the derivative of y, I get the first derivative. So these are solutions to x prime equals ax. Okay, so let's see it in this example. So in this case, I have the matrix A, which is -5, -4, 1, 0. Those are the rows. Let's find the eigenvalues. Well, the characteristic polynomial of this is going to be lambda squared minus the trace, and that's the trace is -5. So I get plus 5 lambda, and then plus the determinant, which is it's minus -4, which is positive 4. And you see, this is the characteristic polynomial of A. And I set that equal to 0 to find the eigenvalues. And that's the same as the characteristic equation here, except I just use R instead of lambda. So that characteristic equation really is from the characteristic polynomial of this matrix. And we solve this, we get that lambda is -1 and -4. And now let's find the eigenvectors. So for lambda equals -1, I get this eigenvector v1, which is -1, 1. Should we just write a few more steps? If I do a plus I, so a minus lambda I, then I get -4, -4, 1, 1, and then I can check that -1, 1 is an eigenvector. And then for a lambda equals -4, then I do a plus 4i, I get -1, -4, 1, 4, and then I check that an eigenvector is going to be 4, -1. And so therefore, I get the two solutions are x1, which is v1, so that's -1, 1, e to the lambda t, that's e to the minus t, and then x2 is v2, 4, -1, e to the minus 4t. And so this is going to be negative e to the minus t, e to the minus t, and then x2 is going to be 4 e to the minus 4t, negative e to the minus 4t. But since my x is just y prime and y, I'm trying to solve for y. And so I see that I get two solutions for y, e to the minus 4t and negative e to the minus 4t. I guess I could have made my x2 4 and I could have made them -4 and 1. That might be easier. Okay, so maybe we'll just change my x2 to -4, 1. So -4 and then 1. Either way, I get these two solutions, and then my general solution is going to be a multiple of the first one plus a multiple of the second one. So these constants in front of the t's, those are my eigenvalues of this matrix A. And this is just a taste of, this is just the easiest example of using matrices to solve differential equations. You can write any second order constant coefficient linear differential equation using matrices like this, but you can solve more general systems of differential equations. So you could have something like x1 prime is 4x1 minus x2, x2 prime is x1 plus x2. So maybe x1 and x2 are the population of certain species at time t. And the population of the first species is somehow dependent on the population of the second species, and vice versa by these two equations, these two differential equations. And we want to figure out the possible functions of x1 of t and x2 of t, so we can see what happens to the populations of the two species over time, for instance. Then we can write this system of differential equations like this. And then if we call this vector x and this vector, that's going to be x prime, the derivative of the first vector. And then I have my matrix A, and then I just do the same thing. I can find the eigenvalues and eigenvectors of this matrix A, and that will give me the solutions of this system of differential equations. So I just wanted to give an example of how these eigenvalues of matrices show up in differential equations. And actually you can see that since I have two negative eigenvalues, going back to this previous example, if you let t get really large, right, what's happening to y? It's approaching 0, right? Because I have these two exponentially decaying functions. So y is going to go to 0 as t goes to infinity. And the more negative the eigenvalues are, the faster that y will go to 0, right? Anyway, the point is that you can use eigenvalues to solve these systems of differential equations. And that's one instance of where you see eigenvalues in applications.